Hello friends, welcome back to my channel. In this video, I'll be discussing diffusion through solids. In my earlier videos, I have discussed molecular diffusion through fluids, that is molecular diffusion through gases and liquids. You can watch my earlier videos on my YouTube channel. So today in this video, I will be discussing diffusion through solids. So first, let me tell you, after watching this video, what will you learn? You'll understand the importance of diffusion through solids, why it is necessary for chemical engineers to know about diffusion through solids. Then you'll also come to know about categories of diffusion through solids. There are two categories. In first category, we have diffusion that follows Fick's law, or diffusion that occurs according to Fick's law. And in the second category, you have that diffusion which do not follow Fick's law. Fick's law, uh, while discussing molecular diffusion in fluids, I have talked about Fick's first law for molecular diffusion. So some diffusion through solids takes place according to the Fick's law. That is, in those cases, the rate of diffusion is directly proportional to concentration gradient. And in this video, I will be talking about the first category. So for that, first we will understand how we can apply Fick's law for diffusion through solids. And after that, after understanding how to apply the Fick's law to diffusion through solids, we will discuss three cases. We will understand three cases. First case is we will talk about diffusion through a solid slab at steady state. So whenever you have a solid slab, for example, and diffusion is one of, say, some component is diffusing through that solid slab. For example, let us say that you have a solid slab like this, and let us say component A is diffusing through it. So for this particular diffusion, we will be getting an equation that will help us in calculating rate of diffusion. Rate which will be given in, say, for example, kilomole per hour or kilomole per second, something like that. Again, the case will be discussed at steady state. That is, we will be getting an equation for RE that is constant, that is not changing with time. Then the second case that I will be discussing today is diffusion through the wall of a cylinder at steady state. So in chemical engineering, there are occasions when fluids are passed through pipes. So for example, if you have a rubber pipe, or let us say if you have a pipe made up of some polymer, then it will be having let me draw it once again so that you'll understand it. So let us say that you have this pipe. So there will be outer diameter for the pipe and inner diameter for the pipe, and there will be some length for the pipe. Okay. So as the fluid, that is, it could be a liquid or it could be a gas, if it flows through the pipe, then it is quite possible that this liquid may be lost through the surface of the pipe. So that means if liquid is flowing through the pipe like this, then it can diffuse. It is possible that the liquid may diffuse through the pipe wall and get lost into the atmosphere. So this discussion, that is our discussion on diffusion through wall of a cylinder at steady state, will give us an equation for calculating rate of such diffusion. So if we are able to calculate rate at which the fluid gets lost through the surface of the pipe, then you'll be able to estimate the amount of loss in terms of money. So in that way, this discussion is going to help us. In short, through this discussion, we will be getting an equation for calculating rate of loss of a component or rate of diffusion of a component through a wall of a cylinder or through a wall of a pipe. Again, we are going to do that discussion at steady state. That is, the rate that we will be getting will be it will not change with time. It will remain constant with time. So this is the second case that which I'll be discussing in this video. Then the third case is I'll be talking about diffusion through the wall of a spherical shell or a sphere. Diffusion through the wall of a sphere at steady state. So again, there are spherical vessels in which liquids or gases are stored. So when you have a spherical vessel and when you are storing some chemicals, like you are storing some liquid or gas in it, then the stored component may diffuse through the wall of the spherical vessel and it may get lost into the atmosphere. Again, in this case, it is important for us to know the rate at which loss is occurring. So here also we will be getting an equation for calculating rate of diffusion through the wall of the sphere, that is Ra. And again, this Ra will not depend on time, that is, it will remain constant, it will not change with time. So this discussion will be at steady state. Okay, so this concepts we are going to understand in this video. First, we will understand the importance, then we will know categories of diffusion through solids. As I said, there are two categories. Out of this, first category includes that diffusion which follows Fick's law. So first we'll understand how Fick's law can be applied for such diffusion. Then for this case, we will, for this particular category, that is for solid diffusion that follows Fick's law, we are going to consider three cases: diffusion through a solid slab, diffusion through the wall of a cylinder, and then diffusion through the wall of a sphere. All the three cases will be discussed at steady state, where the rate of diffusion is not going to change with time. Okay, so let us continue. So first, let us understand the importance. So I have given title to this discussion as introduction. So in this we are going to understand the importance of diffusion through solids. Now, in chemical engineering, you have many operations which involve contact of solid and fluid phases. That is, contact of solid and liquid phases, or contact of solid and gas phases. There are many such operations. Which are this? Which are this? Let us list important ones. For example, leaching. So you can easily tell in leaching, uh, one one or more components from a solid mixture are recovered by preferentially dissolving them into a liquid which we called as solvent. That means in leaching you have solid phase that is contacted with a liquid phase. Okay. So one of the component, one or more component from the solid mixture, let us say that this is a mixture of A and B, and you want to separate them. Rather than saying separation, let us say that we want to recover A from this solid mixture. Then what is done? The solid mixture is contacted with the liquid phase. The liquid that is used in this operation, we call that as solvent. Okay. Now the selected liquid is such that it will preferentially dissolve A in it. Rather than dissolving B, it will give preference to A. That means majority of A will then be diffusing through this solid phase, and then it will be getting dissolved into the solvent, or the solvent may be going to the sites where A is available. A will be then dissolving into the solvent, and the resulting solution will then be diffusing through the solid phase, and then it will be coming into the bulk liquid. So in any case, some diffusion is going to occur through the solid phase, and in order to get the rate of mass transfer in this process, we should know the rate at which you should we should have some knowledge of how components get transferred through the solid phase. Okay. Another example where solid and fluid phases come in contact with each other, example is drying. So drying, we by here we especially mean drying of wet solids. So let us say that you have this wet solid where you have moisture content within the wet solid. So there may be some moisture on the surface. So what is done? This wet solid is contacted with hot air. Hot air or hot gas is passed over the surface of the wet solid. Okay, so what is the result? Result is this moisture will be getting vaporized, will be getting evaporated into the hot air or hot gas, and then it will be removing those vapors. Okay, for the moisture that is present on the surface of the solid, there is no any diffusion through solid involved. But if you talk about moisture that is present within the solid, say for example over here, then before getting vaporized, before getting evaporated, this moisture will have to move through the solid and then come to the surface. The moisture will have to move through the solid, come to the surface, and then it will be evaporated. So here also the moisture is diffusing through the solid. It is coming to the surface and then it is getting lost into the, or it is getting vaporized, and those vapors will be removed by the hot gas. So point is, in drying also, in drying of solids, drying of wet solids, there is contact of solid phase with the gas phase, and there is some diffusion that occurs through the solid phase. Okay. Then other example for this is adsorption. So adsorption, you know, it is a separation operation in which components of a liquid solution or a gas mixture, they are separated by contacting with a suitable solid. The solid in that case is called adsorbent, and it has ability of preferentially concentrating specific substances on its surface. Say for example, let us understand, let us say that this is the adsorbent. This is adsorbent, for example. Let us understand the concept adsorbent. And this is contacted with a gas mixture of say A and B. So you have A in it and you have B in it. Now the selected adsorbent has ability to preferentially concentrate A on its surface. So after some time, uh, most of the A will be getting adsorbed on the surface of the solid. And then after coming onto the surface of solid, there may be some diffusion of A through the solid phase. So here also diffusion can occur through the solid phase. There is a possibility. Okay, so adsorption also involves contact of fluid and solid phases, and there is a possibility of some diffusion through solid phase in that case also. Okay, then another example where you have contact of solid and fluid phases, you have various membrane separation operations. So membrane separation operations, you know the principle of those operations. So you have a membrane that is made up of variety of materials. It could be made up of different materials, and on one side you could have a liquid solution, or you could have a gaseous mixture. Okay, so, for example, let us say that on one side you have mixture of A and B again, A and B. Okay, and the membrane selected has an ability to allow only A to pass through it. It is permeable to A. Okay, so depending on what operation is involved, you have different membrane separation operations. You have reverse osmosis, you have ultrafiltration, you have nanofiltration. So depending on what operation is involved, so for example, if it is reverse osmosis, then how A will move through the membrane. Say A will be coming onto the surface of the membrane, and depending on its solubility in the membrane, it will be first dissolving into the membrane, and after dissolving into the membrane, it will be diffusing through the membrane. It will be diffusing through the membrane. So that means in this case also there is diffusion through solid phase. In membrane separation operations, there is a contact of solid and fluid phases. It could be solid and liquid phase, it could be solid and gas phase. So in either of the cases, diffusion is going to occur through solid phase. Okay, so in order to these are the most you can say few important examples where you have contact of solid and fluid phases. So in each of these cases, you need to have some knowledge of diffusion through solid, or you should know how diffusion through solid occurs in order to find out the rate of the process, rate of mass transfer that is involved in these processes. Okay, so that's why, since many chemical engineering operations involve contact of solid and fluid phases, and through this contact there is some diffusion through solid phase, we should know. Therefore we chemical engineers should have knowledge of how diffusion occurs through solids. So in all these cases, all these four cases that I have listed, some diffusion is going to occur through solid phase. Okay. Okay. Now, if let us compare diffusion through solids with diffusion through fluids. Now we are understanding diffusion through solids. Earlier I have discussed diffusion through solid fluids. So how to compare these two? So if you compare diffusion through fluids, if you compare diffusion through solids with diffusion through fluids, the first thing that you have to note is diffusion through solids is complicated as compared to diffusion through fluids, where you can have, for at least for molecular diffusion, you can have equations for calculating uh, rate of diffusion. I can say you can have relatively simple equations for calculating rate of diffusion, but in case of solids the diffusion is complicated, so equations will not that be simple. In short, diffusion through solids is a complicated phenomenon. Then another important thing that I have to note for diffusion through solids is, as compared to diffusion through fluids, diffusion through solids is a slow process. So we have understood in molecular, if you talk about molecular diffusion in fluids, then rate of diffusion in gases is more than rate of diffusion in liquids, and then rate of diffusion through fluids is greater than rate of diffusion through solids. Okay. So if you compare rate of diffusion in gas and liquid, then rate of diffusion in gas is always higher, and if you compare rate of diffusion through fluids, that is gas and liquid and solids, then rate of diffusion through fluids will always be higher. So that's why we have to note this. Diffusion through solids is slow, that is rate of diffusion through solids is low, less as compared to that through fluids. Okay, so at the end of this particular slide, we have understood the importance of diffusion through solids, and then we have done a simple comparison with diffusion through fluids. And let us so now let us discuss the categories of solid diffusion. I have already talked about it just now, but let us understand it in somewhat details. Okay, so categories of solid diffusion. So you have two categories for diffusion through solids. Which are these two categories? First category includes diffusion that follows Fick's law, or diffusion that happens according to Fick's law. And the second category is that diffusion which does not follow Fick's law. And we are going to talk about the first category in this particular video. So you have diffusion that follows Fick's law, and then you have diffusion that does not follow Fick's law. In this video, we are going to discuss the first category. In coming videos, I will be discussing the second category. In the first category, you have rate of diffusion that is independent of the nature of the solid. The rate depends on concentration gradient. So whatever may be the solid, rate will always depend on concentration gradient. To be more perfect, rate will be directly proportional to the concentration gradient. Okay. So in first category, where Fick's law is followed, rate of diffusion is independent of the nature of the solid. It depends on the concentration gradient. Whereas for the second category, second type, you have rate that depends on nature of the solid. So nature of the solid through which a given component is diffusing, the nature of the solid will decide the rate. The nature of solid will make the diffusion process slow or fast. Concentration gradient is not that important. Structure of the solid is important. So rate depends on the structure of the solid, and it also depends on how the diffusing substance interacts with the solid. So for example, if say component A is diffusing through a solid, then how this A, this component A reacts with the solid, that also has a major role in deciding the rate of diffusion. Okay, so in second category of diffusion, where Fick's law is not followed, structure of the solid is important. So you have diffusion through polymers in a different way, diffusion through crystalline substances, crystalline solids in a different way, diffusion through porous solids in a different way. Another factor that comes into picture in this case is interaction of the solid with the diffusing substance. So for example, in reverse osmosis, the diffusing substance will be first dissolving into the membrane, semi-permeable membrane, and then it will be diffusing. So how interaction occurs between the diffusing substance and the solid, that also decides, or that also affects the rate of diffusion. Okay, so as I said, in this video we will be discussing the first category, that is diffusion that follows Fick's law. So next we are going to understand how you can apply Fick's law for diffusion through solids. We'll understand that. Okay, so diffusion according to Fick's law. Uh, so first we should know that when you can apply the law, when you can apply Fick's law. So law is applicable in the following cases. First, if the diffusion is taking place at constant rate, that means rate of diffusion is constant, that is diffusion is taking place under steady state conditions, there you can apply Fick's law. Then the diffusion coefficient is independent of the concentration. So in those cases where the diffusion coefficient is not dependent on concentration, there in those cases you can apply Fick's law. And another important you can say condition is there should be no bulk flow. So you can apply Fick's law for those diffusion that involves no bulk flow of the diffusing substance. Okay, so under these three conditions you can apply Fick's law for diffusion through solids. Diffusion occurs at constant rate, that means you are dealing with steady state. Then the second requirement is diffusion coefficient is independent of the concentration, it is not going to depend on concentration, and there is no bulk flow. So if there is bulk flow, then you cannot have the dependency, that means rate in that case will not be directly proportional to concentration gradient. You will not be able to correlate it in a perfect way if there is bulk flow. So for the Fick's law to be applicable, there should be no bulk flow through the solid. Okay, now let us know how you can apply Fick's law for diffusion through solids. So how it is stated, let us understand. So the law states that rate of diffusion of a component through a solid per unit its cross sectional area is directly proportional to the concentration gradient, and diffusion occurs in a direction of decreasing concentration. Okay, so the law can be stated like this. You can state the law like this: rate of diffusion of a component through a solid, that means if a component is diffusing through a solid, then its rate, that is measured per unit cross sectional area of the solid, rate of diffusion of a component through a solid per unit its cross sectional area, that rate is directly proportional to the concentration gradient, and diffusion occurs, that diffusion occurs in a direction of decreasing concentration. Okay, so the law can be stated in this way: the rate of diffusion of a component through a solid per unit its cross sectional area is directly proportional to the concentration gradient, and diffusion occurs in a direction of decreasing concentration. Okay, so let us continue with the law. We have just understood how Fick's law is stated for diffusion through solids. So if you you have to represent the law in a mathematical form, you can do it in this way. Okay, so if you consider diffusion of component A in z direction, so let us say that component A is diffusing in z direction. So let us say that this is x direction, this is z direction, and this is y direction. So you have z direction, you have y direction, and we are talking about component A diffusing in z direction. Its diffusion in x direction is neglected, or A is not diffusing in x and y direction, it is just diffusing in z direction. So for this particular case, how to apply the law? So for diffusion of component A in z direction, it will be, the law will be stated like this: rate of diffusion, rate of diffusion per unit area. So rate of diffusion Ra per unit area divided by A is directly proportional to concentration gradient in z direction. So it is dCA by dz. This is true when A is not diffusing in other two directions, x and y. If it was doing that way, that means if it was diffusing in all the three directions, then you will have to have a partial derivative over here instead of having a total derivative. But since we are saying that A diffuses only in z direction, we have a total derivative. So mathematically, the law can be stated by this particular equation. So rate per unit area is directly proportional to concentration gradient in z direction. And if you remove the proportionality, you'll have to have a proportionality constant. In that case, the law will be written as Ra upon A is equal to minus dA dCA by dz. So the terms involved in the equation, what are the terms involved? Ra is the rate of diffusion. For example, it could be moles per unit time, rate of diffusion. A is the cross-sectional area of the solid. Then dCA by dz is concentration gradient in z direction. How concentration of A changes in z direction. Molar, over here Ca is molar concentration. So concentration gradient in the z direction. Then dA is the proportionality constant, and you know this proportionality constant will be diffusion coefficient. The proportionality constant, that is called diffusion coefficient. So if you remember, uh, in case of molecular diffusion through fluids, we had, say for example, if you had a mixture of A and B, then we used to talk about diffusion coefficient of A and B, A in B, or you have diffusion coefficient of B in A. That means B, component B may also be diffusing, component A, both the components will be diffusing. So component A will have its diffusivity in B and B will have its diffusivity in A. But in this case, solid is not going to diffuse, only the component will be diffusing. So that's why we are using this notation for diffusion coefficient in the case of diffusion through solids. Da stands for diffusion coefficient of A, or simply diffusivity of A through the solid. Okay. And then another important thing is we need to understand the significance of negative sign. And after knowing Fick's first law, for molecular diffusion, you can easily tell the negative sign indicates that diffusion occurs in a direction of decreasing concentration. So diffusion will be taking place from a point of high concentration to a point of low concentration. So in order to indicate that, we need to have a negative sign over here. Okay, so negative sign indicates diffusion occurs in a direction of decreasing concentration. Okay, so after knowing how to state Fick's law for diffusion through solids, and then how to apply or how to represent it mathematically, now let us discuss those three cases which I talked about earlier. The first case is steady state diffusion through a solid slab. So for steady state diffusion at a constant rate through a solid slab, how to get rate of diffusion? So at the end of this discussion, we will be having one equation that will help us, or that will allow us to calculate rate of diffusion through a solid slab. So for that, we will consider a solid slab. So you can see you have a solid slab over here. Let this dimension be B, this dimension be L, and this dimension be W. And let us say that component A is diffusing in this direction. So component A, it is diffusing. So over here on this side you have component A, and then component A is diffusing through the solid, and then it will be diffusing to this face. Okay, so for this diffusion, the area that is available for diffusion will be area of this face, the area of this face. And what is this area? How to calculate this area? This is simply L into W. So area for mass transfer in this particular case, area for diffusion, area through which diffusion occurs is L into W. Okay, so let us just look at this face. So what you are seeing in the second diagram is this face. So A is diffusing. Let this end be Z is equal to 0 plane, and this end be Z is equal to Z plane. And A is diffusing from a point where its concentration is Ca1 to a point where its concentration is Ca2. So A is diffusing from from a point where its concentration is Ca1 to a point where its concentration is Ca2. That is one more way of understanding this is A is diffusing from the plane Z is equal to 0 where its concentration is Ca1 to a plane Z is equal to Z where its concentration is Ca2. Okay, so over here we are in the second diagram we are seeing this face. So the length of the diffusion path will be B, that is the length of this dimension from Z is equal to 0 to Z is equal to Z. Okay, so as I said earlier, area for mass transfer, area through which diffusion occurs is L into W. So this face area is the diffusion is taking place through this surface, and that's why area available for diffusion is L into W. Now according to Fick's law, we just have understood mathematically the law is stated as Ra upon A is equal to minus dA into dCA by dZ. And if you rearrange it, how to arrange it, So I'm arranging it like this: Ra into dz. So this dz I have brought on this side, and I have taken this a onto the other side. That is, now you have dz on the left hand side and a on the right hand side. So let us call this as equation 1. Okay, now what can we say about equation 1? You have this differential terms dz and dca. So this is a differential equation. Variables are ca and z. That is a differential equation that tells us how ca changes with z, how ca is going to change with z. Okay, so you have equation 1. The equation is rewritten once again: Ra into dz is equal to minus dA into A into dCA. That was equation 1. Now what are the limit? If you have to get equation for the rate, that is equation for Ra, we need to solve it. And for solving differential equation, we need to know the limits on the variables. Variables are ca and z. We need to know limits on ca, and we need to know limits on z, and those limits will be clear to you from this diagram. So at z is equal to 0, that is at the plane z is equal to 0, ca has a value of ca1. Whereas at the other plane, that is at z is equal to z, ca has a value of ca2. So these are the limits. At z is equal to 0, ca is ca1, and at z is equal to z, ca is ca2. Now let us use this limits and integrate equation number 1. So if you integrate equation number 1, you have integration from 0 to z Ra into dz, that is equal to integration from ca1 to ca2 minus dA into A into dCA. Okay. Now let us try to find terms that remain constant so that they will be coming out of the integral. So since we are discussing the diffusion at steady state, what is the case? Ra is constant, rate itself is constant, so that will be coming out of the integral. Then along with that, dA is also constant, the diffusion coefficient is constant, and area is also not going to change, area is constant. So all these three parameters, that is rate, diffusion coefficient, and A, all these three will be coming out of the integral, and accordingly you have Ra into integration from 0 to z dz. Now Ra is taken out, that is equal to minus dA into A, that is dA and A, they have come out of the integral. So it is minus dA into A integration from ca1 to ca2 dCA. Okay. Now can we absorb this negative sign? So if you have to absorb this negative sign, or if you have to make it plus, then for that you need to change the limits. So upper limit will become lower limit, and lower limit will become upper limit. So ca2 will come over here and ca1 will go over there. Okay. So next, in the next step, that is done. So from the previous, I'm rewriting the equation once again. So you have Ra integration from 0 to z dz, that is equal to minus dA into A integration from ca1 to ca2 dCA. Now let us absorb the negative sign. So if you do that, you have Ra into integration from 0 to z dz is equal to dA into A integration from ca2 to ca1 dCA. So now you can see the limits have changed their positions. Lower has become upper and upper has become lower. And now you just integrate it. So integration of dz is z. So it will be Ra z limits 0 to z, that is equal to dA into A ca limits ca2 to ca1. And finally you just use the limits. So you have Ra into z minus 0, that is equal to dA into A ca1 minus ca2. If you rearrange it, you have Ra into Z, Z minus 0 is Z, so it will be Ra into Z, that is equal to dA into A into Ca1 minus Ca2. In the next step, we can take Z on the other side, that is on the right hand side. So you have Ra is equal to dA into A divided by Z, then into Ca1 minus Ca2, and that is the final equation that will give us rate of diffusion through a solid slab at steady state. A is, I have told you how to get A. For this case, it is L into W. If you remember the diagram, A is length into width. Okay, so this equation, by using this equation, you'll be able to find out rate of diffusion through a solid slab. Okay, now discuss the second case. Let us discuss the second case. What was the second case? Second case was diffusion through the wall of a cylinder at steady state. Steady state diffusion through the wall of a cylinder. We just saw, we just derived equation for rate of diffusion through a solid slab at steady state. Now let us get an equation for calculating rate of diffusion through the wall of a cylinder under steady state condition. So we are going to discuss diffusion at steady state. So let us consider a cylinder like this. So you can see what you see is a section of a pipe, for example. So it is a cylinder. You have inner diameter of the cylinder and then outer diameter of the cylinder, and if something is flowing through it, then there are chances that it will be diffusing out through the surface. So for this particular case, for this particular situation, we are going to get an equation for calculating rate at which this happens, rate at which diffusion occurs through the wall of the cylinder. Okay, so now let us show a proper schematic for this. So what you are seeing over here is the pipe. You have inner diameter of the pipe and then outer diameter of the pipe, and then cylinder shown from a different view. So you have inner diameter, you have outer diameter, and this is the length of the cylinder. This is inner diameter and this is outer diameter. So this is inner diameter. Let me first use radius. So Ri is inner radius and Ro is outer radius. So let us talk in terms of radius. So Ri is inner radius, R0 is outer radius. So on this view also you have inner radius and outer radius. Then this is the length of that cylinder, and let that length be L. Okay, so you have this situation. So you have a cylinder which has inner radius. We have defined inner radius as Ri, outer radius as Ro, and then we are saying that length of the cylinder is L. So again I am showing the diagram. So you have inner radius, you have length L, outer radius, I'll just talk about it. So you have outer radius R0, inner radius Ri. At the inner surface, you have concentration of A. Let us say that we are saying that A is flowing through this section, cylindrical section, and at the inner surface concentration of A is Ca1, whereas at the outer surface concentration is Ca2. So after diffusing through the solid wall and after coming on the outer surface, it may get lost into the atmosphere, in which case we can say that this will be zero, because as soon as A comes on the outer surface, it will be immediately removed by the air that is outside the cylinder. Okay, so you have inner radius Ri, outer radius R0, A is flowing through it. On the inner surface, concentration of A is Ca1, on the outer surface, concentration of A is Ca2, and length of the cylinder is L. Okay, so let us move ahead. Now, in this particular case, as the diffusion occurs, the mass transfer area that is available, it is going to change with radius. So mass transfer area will be the surface area, and the surface area, as you move from the inner surface to the outer surface, radius will change from inner radius to outer radius, and accordingly area, that will be area through which diffusion is going to occur, it is going to change. So that's why we are saying mass transfer area changes with radius. So if you talk about some radius r, then the mass transfer area is given as A is equal to 2 pi r L, the surface area of a cylinder, 2 pi r L, where r changes from Ri to R0, that is inner radius, to the outer radius. So area for mass transfer in this particular case is A is equal to 2 pi r L. Further, Ca, it is very much clear, as you move from inner to the outer radius, Ca also changes. Ca changes from Ca1 to Ca2. The concentration gradient in this case is in radial direction. That means concentration gradient is along the radius. Change in concentration occurs in the radial direction. Now, for this particular case, we need to rewrite Fick's law in a different form. And what is the form in this case? Law will be written as, the Fick's law will be written as Ra upon A is equal to minus dA upon A into dCA by dr. You need to show how Ca is now changing with R. How Ca is changing with R. And if you use area, which is 2 pi RA, for any radius r, then the equation will be Ra upon 2 pi RL, that is equal to minus dA dCA by dr. Now let us continue with this equation next. Okay, so we had just written this equation Ra upon 2 pi RL, that is equal to minus dA into dCA by dr. So if you rearrange this equation, you'll write it like this. So what is done, dr is brought on this side and all other terms are taken on the right hand side. So you have Ra into dr upon r is equal to minus 2 pi LD A into dCA. And if you call this as equation 2, you can easily tell equation 2 is a differential equation. Variables are Ca and R, that means Ca is changing with R. And what are the limits to solve equation number 2? Again, those limits will be clear to you from this diagram. So when R is Ri, that is at the inner surface, concentration is Ca1, whereas at the outer surface the concentration is Ca2. So at R is equal to Ri, Ca is Cai. At R is equal to R0, Ca is Ca2. These are the limits with which we need to solve the equation. Now let us integrate it. So this will be, on the left hand side, you'll have integration from Ri to R2, Ra into dr upon R, that is equal to integration from Ca1 to Ca2 minus 2 pi L dA into dCA. Okay. Now the next step is we will identify the constant terms and we will take them out of the integral. So let us do that. So you have, again, we just saw, we got this equation. Now we need to remove the constant terms out of the integral. So let us do that. From the previous slide you had this equation, integration Ri to R2 Ra d into dr upon r, integration Ca1 to Ca2 minus 2 pi L dA dCA. So at steady state we are identifying constant terms. So at steady state rate is constant, that is Ra is constant. Along with that, diffusion coefficient and L both are constant, so they are also going to come out of the integral. So therefore you have Ra, now it has come out of the integral, Ra into integration from Ri to R2 dr upon r, that is equal to minus 2 pi L dA. All constants have come out, pi is a constant, so all the constant terms are now out of the integral, and you just have 2 minus 2 pi L dA integration from Ca1 to Ca2 dCA. Now as was done in the previous case, we will absorb the negative sign, and we will do that by interchanging the limits. Up, lower will become upper and upper will become lower. So it will be Ra integration from Ri to R2 dr upon r is equal to 2 pi L dA integration from Ca2 to Ca1 dCA. Sorry. So now we have changed the limits. Upper has now become a lower limit and lower limit has now become upper limit. So in the next step we will be integrating it. So from the previous slide we just have this equation where the negative sign was absorbed and you had this equation. Now let us integrate it. So this will be integration of dr upon r is ln of r, so it will be Ra into ln of r, uh, limits are from Ri to Ro, that is equal to 2 pi L dA, integration of dCA is Ca, and limits are Ca2 to Ca1. Then you can use the limits, so it will be Ra into ln of Ro minus ln of Ri is equal to 2 pi L dA into Ca1 minus Ca2. Then you can use the logarithmic identity over here. What is the logarithmic identity? Let me tell you. So if you have natural ln of A minus ln of B, this is nothing but ln of A upon B, the logarithmic identity. So ln of R0 minus ln of Ri is ln of R0 upon Ri, that is equal to 2 pi L dA into Ca1 minus Ca2. Okay, so now let us uh, simplify it further. So you have now what we will just carry out this action. We are going to divide, and in order to put it in a proper form we are doing this. So we are dividing and multiplying the right hand side of this equation, that is this side of the equation, with this term R0 minus Ri, the difference between outer radius and inner radius, the thickness you can say. So if you do that, you have Ra into ln of R0 upon Ri, that is equal to 2 pi L dA Ca1 minus Ca2, and now we have multiplied with R0 minus Ri, and at the same time we have divided with R0 minus Ri. So in the next step we will rearrange it, we will put it in a different form. So it will be Ra into ln of R0 upon Ri, that is equal to 2 pi L. So the term with which we multiplied, I have brought this term over here, so it will be 2 pi L R0 minus Ri into dA Ca1 minus Ca2 upon R0 upon R0 minus Ri. So in the next step I am writing it like this. So Ra is equal to 2 pi L. Now the logarithmic term I have brought to the right hand side, so it is 2 pi L R0 minus Ri divided by ln of R0 upon Ri. Then other terms remains as they were earlier, so it is into dA Ca1 minus Ca2 divided by R0 minus Ri. Okay, so next we just got this equation. Ra is equal to 2 pi L R0 minus Ri divided by ln of R0 upon Ri into dA into Ca1 minus Ca2 divided by R0 minus Ri. Now I will write it in a different form once again. So it is Ra is equal to 2 pi R, sorry, 2 pi L R L M. Now I'm trying to replace this group R0 minus Ri divided by ln of R0 by Ri with this RLM. So now I have Ra is equal to 2 pi L R L M into dA Ca1 minus Ca2 divided by R0 minus Ri, where in this case RLM is nothing but R0 minus Ri divided by ln of R0 upon Ri. Again, I will write it in a different form. Now I'm writing it like this: Ra is equal to AC into dA divided by R0 minus Ri into Ca1 minus Ca2. That means I have replaced some terms in the previous equation with AC, and you can easily identify which are those terms. So I have replaced 2 pi L RLM, 2 pi RLM into L. I have replaced with AC, which is the area through which diffusion is going to take place for this particular case. So for diffusion through the wall of a cylinder, area through which diffusion occurs is 2 into pi into RLM into L, whereas RLM is a logarithmic average. RLM is the logarithmic average of inner and outer radius of the cylinder. Okay, that is the mass transfer area, that is area available for diffusion. The length of the diffusion path is this thing, thickness of the cylinder, that is R0 minus Ri. So in this way we get an equation at the end of discussion. For this particular case we get an equation where now we will be able to calculate rate with all the terms present in the equation known to us. So Ra is equal to AC into dA divided by R0 minus Ri into Ca1 minus Ca2. Okay, now let us discuss the last case. And what is that? Diffusion through a spherical shell, or diffusion through the wall of a sphere. So we are going to discuss radial diffusion at steady state through the wall, diffusion in radial direction. In the previous case, that is diffusion through cylinder wall, that was also in the radial direction, so that was also radial diffusion. This is also radial diffusion. So radial diffusion at a steady state will be discussed. So for that we are going to consider a sphere like this, a spherical vessel, you can see. So if you cut through it, you will have inner diameter for the vessel or shell and outer diameter for the shell. Let us talk in terms of radius. So you have inner radius Ri, outer radius R0, and then at the inner surface, as we have understood earlier during our earlier discussion, Ca1 will be the concentration of A at the inner surface, and Ca2 will be concentration of A at the outer surface. So mostly, since immediately after coming out of the vessel, out of the shell, it will be getting lost in atmosphere, so most of the time it will be zero. So we will understand that in more we can say it will be more clear to you when we solve numericals based on this. Okay, so mass transfer area, again for this case also mass transfer area is changing with R, as it happened in the case of diffusion through wall of a cylinder. Here also mass transfer area is changing with R, and this area, if you talk for any radius say R, the mass transfer area will be given as A is equal to 4 pi r square, which happens to be the surface area of a sphere, you know, surface area of the sphere with radius r. Okay, so this area will be available for mass transfer. So this is I have noted that there was no need of just one. Give me 1 minute. So you have surface area of a sphere with radius r. Okay, then CA is changing with r again. As you move from inner radius to outer radius, CA is going to change, or rather CA changes from CA1 to CA2. The concentration gradient again is in the radial direction. That means concentration is changing with r. That means concentration gradient is in the radial direction. So again, for this case also we need to write Fick's law in different form. So how are you going to write that? That will be written as Ra upon A is equal to minus dA into dCA by dr. So in the next step, we are going to replace A with 4 pi r square. In this case, area available for mass transfer, area through which diffusion occurs is 4 pi r square. So you'll have Ra upon 4 pi r square is equal to minus dA into dCA by dr. So in the next step, we are going to rearrange that equation. So I am just once again showing the schematic for the spherical shell. Okay, so Fick's law, now we know, we have just written it in this form. Ra upon 4 pi r square is equal to minus dA into dCA by dr. Let us rearrange it. So after rearranging, we will have this equation. Ra into dr upon r square is equal to minus 4 pi dA into dCA. So what is done? Dr is brought on this side. Dr from the right hand side, now we have got it on the left hand side, and all other terms, that is 4 pi, the remaining two, you say, the term, we have taken it on the right hand side. So you have Ra into dr upon r square, that is equal to minus 4 pi dA into dCA. Okay, let us call this as equation 3. Equation 3 is a differential equation. What are the variables? Variables are CA and R. That means CA is changing with R. What are the limits to solve equation number 3? Again, very simple to understand. At R is equal to Ri, CA is CA1, and at R is equal to R0, CA is CA2. So I have written those. That means when you are at the inner radius, CA is CA1, and when you are at the outer radius, CA is CA2. So if you use these limits and integrate equation number 3, then you get this integration from Ri to R0 or Ro into Ra dr by r square, that is equal to CA1 minus CA2 minus 4 pi dA into dCA. Then what are the terms that are constant? Ra is constant at steady state. Along with that, dA is also constant, so pi is constant, so all this will be coming out of the integral. And then you have r, after you take the constant terms out of the integral, you have Ra into integration from Ri to R0 dr upon r square, that is equal to minus 4 pi dA integration from CA1 to CA2. Okay, so next, again continuing with that equation, we had just got this equation Ra integration from Ri to R0 dr upon r square, that is equal to minus 4 pi dA CA1 to CA2 dCA. Now if you absorb the negative sign, then we will have to change the limits. So in that case, you have Ra integration from Ri to R0 dr upon r square, that is equal to 4 pi dA integration from CA2 to CA1. Now the limits are changed. Okay, so you have, I will write it in r, 1 upon r square is nothing but r raised to minus 2. So you have Ra integration from Ri to R0 r raised to minus 2 dr, that is equal to 4 pi into dA integration from Ca2 to Ca1 dCA. Now let us integrate it. So on the left hand side, integration of r raised to minus 2 is r raised to minus 2 plus 1 divided by minus 2 plus 1, and the limits are from ri to r0, that is equal to 4 pi dA. Integration of dCA is Ca, so it will be Ca with limits from Ca2 to Ca1. Again, if you simplify it, you have Ra into r raised to minus 1 divided by minus 1, uh, limits Ri to R0, that is equal to 4 pi dA into Ca, limits Ca2 to Ca1. So again, this negative sign is absorbed, and for that we have changed the limits. Now limits are from R0 to Ri. Earlier it was from Ri to R0. Now after absorbing this negative sign, we have changed it to R0 to Ri. So you have Ra into r raised to minus 1 R0 to Ri, that is equal to 4 pi dA into Ca from Ca2 to Ca1. ठीक है, so r raised to minus 1 is nothing but 1 upon r, so you have Ra into 1 upon r, limits R0 to Ri, that is equal to 4 pi dA into Ca, limits Ca2 to Ca1. ठीक है, now let us continue with the previous equation. So you had this equation, Ra into 1 upon r, R0 to Ri, that is equal to 4 pi dA into Ca from Ca2 to Ca1, the limits. Now we have to apply the limits. So after applying limits, you have Ra into 1 upon Ri minus 1 upon R0, that is equal to 4 pi dA into Ca1 minus Ca2. So Ra, if you simplify, it will be Ra into R0 minus Ri divided by R0 into Ri, that is equal to 4 pi dA into Ca1 minus Ca2. Further, we will write it in a different form, that is we have written equation for Ra. So Ra will be equal to 4 pi R0 into Ri divided by R0 minus Ri into dA into Ca1 minus Ca2. That is, again I will write it in a different form. So now I have written it like this: Ra is equal to As into dA divided by R0 minus Ri into Ca1 minus Ca2. That means I have used As for some terms that were present in the previous equation. So what is the replacement for 4 pi into R0 into Ri? I have replaced this group with As, and As is nothing but, in this case, it is the area through which diffusion is going to take place. It is 4 pi into R0 into Ri, and this is nothing but the area for mass transfer, that is area through which diffusion is going to take place, and length of the diffusion path is R0 minus Ri, thickness of the shell, spherical shell. Okay, so in this way, now we have an equation that can be used to find rate of diffusion through the wall of a spherical shell. With this, I end my discussion on the third and the last case for this video. In my coming video, we will be solving some numericals, or rather I will be solving some numericals and you solve along with me. Those numericals will be based on the three equations that we have derived in this particular video. Thank you for being with me. Hope you will stay with me. You please watch my uh, various videos on my YouTube channel. For today, thank you for being with me. Have a nice day. Bye bye.